So today we're going to talk about dimensionality reduction. Dimensionality reduction is a technique for taking a data set that has a lot of different variables, a lot of different columns, a lot of different dimensions, and displaying it or breaking it down to a much smaller data set that is easy to view and not necessarily as has significantly fewer dimensions. So I'm going to start off by showing you support vector, or not support vector machines, singular value decomposition. So we have this array here, and we're going to break it down into U sigma VT, as I'm sure you saw in the lectures. So we break it down to three matrices, and this is the core behind PCA is singular value decomposition, where you're decomposing into singular values of the matrix. This is similar to principal component analysis, but for a matrix that's not necessarily square. So let's start off with PCA. We start off with our array of x's. We standardize the data by taking the mean and subtracting it. We compute the covariance matrix, and then we perform eigen decomposition or singular value decomposition if the matrix was not square. We select the top eigenvalues, or the top eigenvectors rather, based on the top eigenvalues. We project the data onto the principal components. Here we get the principal components, we get the reduced data set, and then we can visualize it. So here's our original data, it's in 2 dimensions, and here's our new data, it's across 1 dimension. So we've reduced it to its components of greatest variance by taking the eigenvectors of the covariance variance matrix. So here we take PCA using sklearn. PCA equals PCA, number of components equals 1. Fit the transform. Here we do what's called linear discriminant analysis. This is similar to PCA, and that's the dimensionality reduction technique. Except here we're trying to separate classes, and we're trying to find the smallest boundary, or smallest dimensionality reduction that will separate the classes. So here's an LDA reprojection of the iris data set. And then here we do a similar thing, but we do manifold embedding technique. It's a more complex technique, and as you can see, it separates out even more. So this is TSNE, which is manifold embedding. I'll try and show what this looks like. Basically, you're finding the nearest neighbor in theoretical space, and you're creating well-separated clusters. You're creating a manifold that goes around and around by finding the nearest neighbor within the clusters. So yeah, that's some dimensionality reduction code. Thank you. Hope you have a great day.